When the number of trials for a binomial random variable is sufficiently large, we're actually able to calculate the probabilities by approximating them using the normal distribution. Now, this can be useful for us because the binomial distribution relies on binomial coefficients, or n choose x. And these can be quite challenging to work out, especially if we want fairly large events. So if you want, say, 100 different events, you need to calculate 100 of these different coefficients. You need to add them all up together. They don't simplify down particularly nicely. So instead, we can turn to the normal distribution, which has probabilities that are a lot more straightforward to calculate. That can even be, say, approximated using the empirical rule. But in order for us to do this, we need to adjust for the fact that the normal distribution is a continuous distribution and the binomial distribution is a discrete distribution. So with large numbers of trials, the probabilities from the binomial distribution are challenging to compute. And so if we take n to be large enough, then the binomial and the normal are going to be approximately equal to one another. So thinking about the binomial distribution here, right? If x is a random variable that counts the number of successes on n independent trials, if there's a constant success probability of p, then x is binomial with parameters n and p. This results in the expected value of x being n times p and the variance of x being n times p times 1 minus p. Now, if we consider plotting out this probability mass function, and we take large n, so in this case we'll take n to be equal to 100, then looking at this curve, what we should notice is that if you were to sort of smooth it out here, right? So if you don't think about this as being the staircase, but instead think about this as sort of the smooth curve, this looks a lot like a bell curve, right? There's quite the bell curve structure to this. Or in other words, this looks a lot like it's a normal distribution. Of course, the normal distribution will not have the actual boxes there. It doesn't have a probability mass function, but it looks like it's taking on the same general shape, right? We have a lot more around the mean of it. They tail off into the different tails, right? Sort of fits that bell curve pattern. And so this suggests to us that maybe the normal distribution could be used to approximate the binomial distribution. And so how could we think about this normal approximation here? Well, if we take x to be a binomial NP, then we can define W to be a normal distribution that has the same mean and the same variance. So remember, the expected value of x is n times p, and the variance of x is n times p times 1 minus p. So we'll define W to be a normal distribution that has that same mean and that same variance. Okay, and so now we know that the expected value of x and the expected value of W are the same, the variance of x and the variance of W are the same, right? So now we have this equation here. Then we can use W to actually approximate these probabilities with respect to x. And so if we plot out that PMF of x again, here with n equaling 100 and p equaling 0.25, laying over top of that, we could take the density of the normal that has a mean of n times p and a variance of n times p times 1 minus p. And doing this, we see that there's quite a lot of overlap between these two curves, right? So it's not going to be perfect, that shaded dark green on top of that probability mass function. You can see that, we have sort of areas peeking out here above it, but it's pretty close, and it turns out it's going to be close enough for us to use to approximate these probabilities. If we increase n in size even more, and specifically increasing n relative to the size of p, then this approximation is actually going to improve. And so how big do we need n? Well, a rule of thumb that we can take is that if n times p is greater than or equal to 5, and n times 1 minus p is greater than or equal to 5, then this approximation is appropriate. Sometimes you're going to want to take these to be a higher value, so perhaps being greater than or equal to 10. But taking greater than or equal to 5 is at least going to get us into the ballpark of being able to approximate these probabilities. Okay, and so for each of the following examples, indicate what normal distribution we could use to approximate the given binomial. So in the first case, we have a pollster randomly selects 500 voters to see if they would support a particular referendum. It's known that 60% of all individuals support it. Okay, and so then in this case, what binomial is x going to be following? Well, we're going to be taking 500 independent observations here, and we're going to be taking a success probability of 0.6. And so then if we want to know, well, which normal distribution can approximate this, right, what we need to do is we need to check n times p, right, which in our case is going to be 500 times by 0.6. and that's going to give us 300 here. We also need to check n times 1 minus p, which is 500 times by 0.4. So that's going to give us 200. Right? Both of these are going to be much greater than 5. Okay. And as a result, we can use a normal approximation. So once we know we can use a normal approximation, the question becomes, well, which normal do we use? And we would take W to be a normal. The mean should be n times p, and the variance should be n times p times 1 minus p. Right? We know n times p is 300, so that's going to be a normal with a mean of 300. And then the variance is going to have to be 500 times by 0.6 times by 0.4. Right, so n times p times 1 minus p. And so then you're going to have 300 times by 0.4, which I think is 120. Okay. And so then this is the normal distribution that we're going to use there. Okay, so we checked to make sure that the normal distribution was appropriate, and then we can work out which one it is. So n is 500, p is 0.6, n times p is 300, n times 1 minus p is 200. So then W should be a normal with 300 and 120. Okay, second example here, factory produces light bulbs, wants to understand the number of defective light bulbs in a batch of 150 if 300 or if 53% of all light bulbs are defective. So X here is going to be a binomial. Right, the number of samples is going to be 150. That's the number in our batch. The success probability here, success is it being a defective light bulb, and so that's going to be 3%. And so then what we can check is n times p, which is 150 times by 0.03, which actually gives us 4.5. Okay, and so because this is only giving us 4.5, that's less than the value of 5, and so then we can't use our normal approximation here. Okay, so we don't need to find a W because there's no normal that we should be using to approximate this. Okay, n is 150, p is 0.03, n times p is 4.5, and so no approximation should be used. Okay. Consider part C here. So drugs being tested, 25 patients. It cures 75% of all patients, and interested in the number who are cured. And so then n here is going to be 25. P is going to be 0.75. Right, and so then we can check n times p, and we can check n times 1 minus p. Right, we need both of these to be greater than or equal to 5. And so then we would be checking what 25 times by 0.75, and we need to check 25 times by 0.2. So this is 18.25 and 6.25 or 6.75 respectively. Okay, so both of these are going to actually be greater than 5, and so then we would check or take W to be equal to a normal with a mean of 25 times by 0.75, and the variance is going to be 25 times by 0.75 times by 0.25. Right, so then we can work out exactly what this is, right, plug everything in, and that's going to be the normal that we can take here. Okay, so n is 25.75, so that's 18.75 and 6.25, right? So then W is going to be normal with 18.75 and then 4.6875 as the variance. Last example here, we have a particular plant species, 25% of the offspring have blue flowers. A scientist is counting the number of blue flowers observed on 20 offspring. Okay, and so then we have n is 20, p is 0.25, right? And so then if we take n times p, this is actually going to give us exactly 5. Okay. Now, because it's exactly 5, it's sort of right on the line that we're using. We probably shouldn't use the approximation in this case, but we could technically still justify it. Okay, so if we take n times 1 minus p, that is going to end up giving us 15, right? And so we're fine on the n minus p. That one's sort of a question mark. But if we wanted to go forth with this, right, then W is going to have to be a normal. N times p gives us 5, and then n times p times 1 minus p is going to give us, 5 times by 0.75. Okay. And so then that would give us the W that we could use to approximate here. Okay, so n is 20, p is 0.25, so then 5 and 15 as our breakdown. We could use 5 and 3.75 if we really needed to, but we should know that this is probably a borderline useful approximation. Now, the other thing that we need to think about is the fact that W is a continuous random variable and X is a discrete random variable. And so how does this play into things? If we wanted to know, say, the probability that X was equal to some little x, we can't simply take the probability that W is equal to some little x, since the probability that W is equal to X is always going to be 0. And further, even if we wanted to consider the probability that X was less than or equal to some value little x, we cannot use w being less than or equal to x directly. And the reason is that w is a continuous random variable, right? So because w is a continuous random variable, it can take values between the integers, right? So if you wanted to know the probability that x is less than or equal to 5, well, what do you do with all the values, say, between 5 and 6 that w can take on? Okay, and so because it's continuous, it can take on a wider range of values, and we need to decide what happens with all of those. To overcome this, we use what we call the continuity correction. And the continuity correction is going to come up all over the place in statistics. It's sort of any time we're using a continuous approximation to something that is discrete, we need to think about how to overcome these things. And broadly speaking, the continuity correction is simply rounding, right? So what we ask is, well, what values for w, if we rounded them, would correspond to the event that we care about for x? So we can then calculate probabilities associated with this modified event, and those are going to approximate the probabilities that we're looking for. So for instance, suppose we want to know the probability that x is less than or equal to 5. If w is less than or equal to 5, then x is evidently satisfied, right? If you round off any value less than or equal to 5, you still get something less than or equal to 5. But if w were also 5.4, and then we rounded w, we would still have something that was less than or equal to 5. And so in particular, if we take w to be any value that is less than 5.5, then it rounds to being less than or equal to 5, right? And so then ultimately what we're saying is that the probability that x is less than or equal to 5 is approximately the same as the probability that w is less than 5.5. And so instead of calculating w less than 5.5 or w less than 5, we instead calculate w less than or equal to 5.5. All right, and so this is the type of logic that we're applying for the continuity correction. And so then for each of the following, specify in terms of w an event that approximates the event given in terms of x. All right, so if we want x to be greater than or equal to 3, right, then what we have to ask is, well, what values for w are going to round such that if you were to take them, they're going to give you something that's greater than or equal to 3. And so, of course, we're going to have everything that's greater than or equal to 3, right? That's a given. However, we can actually go lower than that, right? Because if we take it to be greater than or equal to anything for 2.5, right? So w is greater than or equal to 2.5, then anytime you round any of these values, they're going to round up to being greater than or equal to 3. And so x being greater than or equal to 3 means that w should have to be greater than 2.5. And so that should actually say is greater than 2.5. Okay, so we can take a look at another example here, x being less than or equal to 9, right? So then what values are going to round for w so that they would all be less than or equal to 9? And if we take anything that's less than 9.5, then that's going to round down to being less than 9, right? So w less than 9.5. What about for x being greater than 5? The thing to note about x being greater than 5, if we think about how is that different than x being greater than 3, or greater than or equal to 3, right? So the event from part A, the difference is that we don't include 5 here, right? So x being greater than 5 is actually the same event as x being greater than or equal to 6, because if x is greater than 5, we know x is discrete, so it can't take on any value between 5 and 6, and so 6 is the smallest value it can take on. And now once we know x being greater than 6, it's the same type of event as in A, and with A, then what we want here is w to be greater than or equal to 5.5, right? Because then we round up to being greater than or equal to 6. And so this is equivalent to x being greater than or equal to 6, thus w has to be greater than 5.5. Right? Same thing with D. If you think about how is D different than B, right? We don't include this, the equal sign. And so x being less than 15 is going to correspond to the same thing as x being less than or equal to 14. Because if it's smaller than 15, the largest it can be is 14. And so then this is going to correspond to w being less than 14.5. Right? And so x less than or equal to 14 corresponds to w being less than 14.5, right? And so in all of these cases, if you round off the values for w, it's going to give you the correct event for x. The last one that we want to look at here is, well, what if we wanted to approximate the probability that x was equal to 7? And so then we could ask, well, what values are going to round to 7? And if we take anything that is above 6.5 and below 7.5, all of those are going to round into being the value of 7. And so this is actually going to become an interval for W, right? So if we calculate the probability that 6.5 is less than or equal to W, which is less than 7.5, right? This probability is going to sort of correspond to the same thing as X being equal to 7. So it's a little bit different than the other ones, right? But we're still just asking what would round to be the correct value. So no matter whether we're talking about things being greater than, less than, equal to, greater than or equal to, less than or equal to, right? Any of these combinations, we can always convert the event from our discrete into our continuous. And once we've done that, we've applied the continuity correction. Then if we want to approximate the probability, we simply calculate the probability of this new event. So how does that work? Well, let's take a look at this example here. We have a national survey finding 48% of US adult population supports a proposal for a new healthcare reform bill. And a news organization wants to conduct its own random sample, 1,200 adults, asking if they support this measure. And so then we know that in truth, 48% of the adult population supports this proposal, but we want to think about this sample of 1,200 adults. And so what we first want to do is approximate the probability that 550 or fewer adults of the sample support the measure. And so what do we need to do? Well, the first thing that we should do is we should set up X, right? And we know that X is going to be a binomial with n being 1,200 and p being 0.48, right? Because that is our setup of this question here. Okay, and so then we could check to make sure that n times p is greater than or equal to 5 and n times 1 minus p is greater than or equal to 5. In this case, with n being 1,200 and p being right around 50%, both of these are going to be right around 600, right? And so that will be totally fine. I believe that n times p is something like 576, okay? And so we are well over our 5 here, okay? And so then we need to work out, well, what is W? And W is going to be a normal, right? And the mean is going to be n times p, and then the variance is going to be n times p times 1 minus p. And so ultimately, what we want is an event that X is less than or equal to 550. Okay, this is going to correspond to W being less than 550.5. Okay, and so ultimately now what we can say is, well, the probability that X is less than or equal to 550, which if we think about trying to calculate directly, would require us to sum up 550 different probabilities, right? Because you need the probability that X is 0 plus the probability X is 1 plus the probability that X is 2 and so forth, right? That's a very tedious sum for us to take. And so instead we can say, well, this is going to be approximately the same thing as the probability that W is less than 550.5. Okay. And then what we can do is we can use our normal probability tools, right? So that then we can take this to be the probability W minus its mean divided by its standard deviation, which we get using our definition of W up here, is less than or equal to 550.5 minus the mean over the standard deviation. Okay, and ultimately this probability here is the same as the probability that the standard normal is less than or equal to that term, right? Which we can use as phi, 550.5 minus the mean over the standard deviation here. Okay. Once we have this expression, we could either leave it expressed in that way, or we can turn to a calculator or a computer to work out the numeric approximation there. Okay. So walking through all of these steps again here, because n is 1,200 and p is 0.48, the approximation is valid. That gives us a normal with 576 and 299.52 as the mean and the variance. We want the probability that X is less than or equal to 550, which is approximately the same as the probability that W is less than or equal to 550.5 using our continuity correction. So then from normal probability techniques, right, we subtract off the mean, we divide by the standard deviation. That gives us phi of negative 1.473. And so then if we wanted a numeric expression for this, we can turn to, say, R. In R, this is going to be P norm. If you call P norm of negative 1.473, that gives you about 0.0704. And so there's about a 7% chance that fewer than 550 adults, or less than or equal to 550 individuals responding to the survey, would say that they support the new healthcare reform bill. Take a look at part B. What's the probability that more than 800 adults support the measure? And so then here, we want the probability that X is greater than 800, right? And this is going to be the same thing as the probability that X is greater than or equal to 801. Right? Because we want to make this sort of equate. This is going to be approximately the same as W being greater than or equal to 800.5. Okay, and now suddenly we can use our normal probability technique. So this is 1 minus the probability that W is less than or equal to 800.5, not 0.8, 0.5. Okay, and then this we can use our standardization techniques, right? And so then by subtracting off the mean, dividing by the standard deviation, that's going to end up in a normal probability here, right? And so then that's going to be 800.5 minus the mean divided by the standard deviation. Okay, we can plug this in to say p-norm, and we can get our response there. So we're using the exact same approximation technique, except we need to make sure that we've converted the event correctly, right? So that's going to be approximately the same as the probability that W is greater than 800.5. Using those normal techniques, we can look at the complement, and so that's 1 minus 5, 800.5 minus 576 over square root of 299.52. That's going to give us 1 minus the p-norm of 12.9, right? That gives us 0 if you plug that into R. Now, we can also ask, how might we have been able to know that the probability in B should have been approximately 0? Okay, and so if we think about what's going on here, right, we know that our mean of our normal distribution is 576, okay, and our standard deviation is going to be the square root of 299.52. So this is about 17.31, okay? And so if you think about the empirical rule is going to tell us that if you take 576 plus or minus 3 times our standard deviation, so that's 17.31, right? That's going to contain 99.7% of the probability. Now, even without being able to do all of this sort of mental math here, right? Even if you were to take the standard deviation to be 20, right? Just to make sort of the calculations easier here, that means that 60 people plus or minus the mean is going to be almost everyone that is going to be taken in here. And if you take 576 plus 60, you get what, 636, right? And so somewhere between, say, 516 and 536, or 636, sorry, is going to contain almost all of the observations. So if we want to know greater than 800, right, we are well beyond this range here. And in fact, using the math that we've just seen, we're almost 13 standard deviations above the mean, right? Our z-score from the previous question is going to be about 13. And so because we are so far from the mean, the empirical rule tells us that that probability is basically 0. Okay, and so just because of the fact that we can use the normal approximation here, if you had actually been asked this question, you could have, without needing to do any real calculations, worked out that this probability has to be around 0. Okay, so the standard deviation is 17.31. From the empirical rule, about 99.7% of observations fall within 3 standard deviations of the mean. So 99.7% are going to fall basically between 524 and 628. And even if you expand that out, right, even if you went from like 500 to 700, we're still well beyond this range. Okay, and so there's basically 0 probability that you fall outside of this interval. Look at part D here. What is the probability that x exactly equals 600? Okay, so we want the probability of x being 600, right? And if you want this in terms of W, that's going to be approximately the probability that 599.5, so you go down half a unit, is less than or equal to W, less than or equal to 600.5. Okay, and if you want to calculate this using W, we can use our normal probability calculation technique. So that's going to be the upper bound, standardized, minus the lower bound, standardized. Okay, and now this difference in mu could be calculated using our normal probability calculator. Okay, and so if we work out what these values actually are, right, the probability that x is equal to 600, it's the same as W being between, or approximately the same as W being between 599.5 and 600.5. And so then plugging into this gives us the difference between phi of 1.42 and phi of 1.36. Plugging into p-norm, that's p-norm 1.42 minus p-norm of 1.36, and so that's going to give us 0.0091 as our approximation. Now, what is the exact probability that x is equal to 600? And so because we just want one probability here, we can actually work this out, right? That's going to be n, which is 1200, choose x, which is 600, okay, times by p, which is 0.48 to the power of 600, times by 1 minus p, so that's 0.52, to the power of 1200 minus 600, so that's also to the power of 600. And so then if you plug this into a calculator, that's going to give us this exact probability. And so in this case, right, working out the exact probability is actually not too challenging. So we plug that in, that gives us 0.0088. And so ultimately, if you round this off to 3 decimal points, that gives us 0.009, which is exactly what we got in our normal approximation. And so this is a very similar probability using the normal approximation to the binomial. And what we would find is that most events, if you're dealing with an approximation that has n being this large, are going to be fairly accurate in terms of their approximations, right, which justifies the use of this normal approximation. You won't tend to need to use it if you're just looking for a single event, but if you want these ranges of events, it can be quite helpful. So long as we have trials, the number of trials being sufficiently large, the normal distribution can be used to approximate the binomial distribution. We need to make sure we're applying the continuity correction, which is going to allow us to use the continuous values of the normal to approximate the discrete values of the binomial. But applying this continuity correction and checking to make sure that the approximation holds given the specific values that we're dealing with are going to allow us to work with binomial probabilities through all of the normal rules that we have. So that's going to mean that we can use our normal probability calculators, but it's also going to mean that we can use things like the empirical rule to get a rough sense of what's going on, even without calculators handy.